Hi, we're Group 13 and this is Cerberus. Our group is formed by Jorge Pulnes, Paola Londono, Ryan Pennant from Computer Engineering, and Dylan Rivera from Electrical Engineering. Cerberus is a self-propelled robotic car with voice command and object recognition capability. The end result should be able to move in all directions, recognize fixed obstacles, and detect certain trained objects. Some of the essential requirements and specifications that we have highlighted are the car dimensions of less than 225 square inches. The second is the distance sensor reading capability of at least 4 feet. And the third one is that the car can turn away from the obstacle 1 foot from the object. This is what we had in mind when we were working on the design. Here we can see the bottom and the top of the car's first level. Here we can see the second level with the Jetson Nano and the third level with the camera and the microphone. And finally, a profile view on the left and the front view on the right. You might have wondered why the name Cerberus. The 3 ultrasonic sensors in the front of the car gave us the idea.
We began by building our prototype, our car prototype. As you can see here in this image, this is what it would look like, or what it looks like. We also tested the components we ordered. We ordered a couple of main components like the battery, the motor, the sensors, and a board to start testing the movement of the car. And like you can see in this video, we tested our component just like this. Made sure they were working before we started using them. And now I proceeded to design my PCB board. The PCB board would have the function of connecting to our main microcontroller, which is the Jetson Nano, and from here we'll control the sensors and the motors. Knowing this, I created my circuits, as you can see here in Altium Designer, and I did the schematic library first, did every single component, and also made sure each component had its own footprint so that it would translate correctly. Then I built my schematics with all the components connected correctly, made sure they were all connected where they were supposed to go. And from here, then I passed the circuit, the diagram to my PCB board. I made sure the dimensions were good. I made sure the ground planes and the 5 volt and 3.3 volt were good. Now that we made sure our PCB was working, all our rules were working, the design was working, now we proceeded to order the board. Something also cool from Altium Designers, we can view our board in 3D, so it will look something like this in person. Now I proceeded to order it in a page called PCB Way. So first I put in my PCB board, like all the file. It went under review. They made sure it was working they made sure it was good from their side. They had no questions. Went through, I paid for it, and now I'm waiting for it to arrive. It's in production. Should arrive here like 3 days. I also ordered the components to mount them on the PCB and to solder them. The PCB is going to look something like this. This would be the top, this would be the bottom. And so now I'm waiting for the board to arrive, build it, and test it.
Motors and sensors. To test the accuracy of the pins connections, first we used an Autodesk simulation program to integrate the basic components of motors, ultrasonic sensors, powers, motor driver, and Arduino by identifying the correct pins and getting a test code to get it to run. As we can see, the motors and sensors are working. We use the physical prototype. For this, we're using an Arduino Uno and an L293D motor shield. Therefore, the coding part is actually different when using the Arduino code, since it's a particular library in existence to use with this motor shield. Additionally, the sensors pins are connected to the analog pins of the motor shield, and the Arduino new pin library cannot be used in this case. Since the PCB won't have these parts, there is no reason to continue using this method, and we will further develop our code from simulation. This prototype is mostly for hardware testing. For the ultrasonic sensors testing, we can see how they are reaching readings higher than 4 feet. This is good but not necessary, since the new ping library has a function where we can set the maximum reading to be 4 feet. However, this way we can always test our sensors if we run into hardware issues. Additionally, we were able to establish communication between Python and Arduino through our port. The communication is established through the port provided by Arduino. The connection is really slow and we need to work in optimizing it.
So for the voice recognition, we have managed to establish connection with ROS and with our Python files. Uh, we managed to actually translate the words that we want into text so the program can recognize what we want to do, which is move forward, backwards, left, to the right, and to stop. Also to increase speed and to decrease speed. How did we manage this? I'm gonna address that in the next slides. So here for the voice control, I just took several designs that contain controls on how to move a robot in different directions. As you can see, it has to depend on the angular position, also the velocity, and then by just mimicking that, we can just give direction to it. Then we create a voice mapping. So what it does is that every time I say certain word, it's gonna identify that word to a number. When it maps that number to the instructions, it's gonna go to the right, forward, back, and so on. So you can see some of the code for the robot movement, and you can see how it's being programmed to have different states. We also have a joy state, which is really important to pre-test it before implementing the voice recognition, which was to do it with a control remote or a PS4 control. And then we have a simulation, which is not connected yet. We have to work on the simulation because for some reason we can't get to establish the connection between Ross and Gazebo. Here's going to be a little video on how it works. You can see some of the positions for the code, how we're going to make it go to different directions. You can see the numbers right where it says page R is where we have assigned those number mapping the control to the number that is going to identify by the word that we say. And on the left corner, you can see that we have established the connection with the raw server and the code, so it's working perfectly. It recognizes the words. There's a log that can identify most of the words, and some of the words have a tiny fell error when we say them, but it needs to be fixed.
For our object detection, we used Google's TensorFlow to build a real-time object detection model that allows for a constant video stream to be consistently analyzed in order to determine what objects lie in the path of our robot. We were able to use open-source pre-configured assets from the TensorFlow model garden in order to model objects for the camera to perceive. In these images, you can see that the trained model we have thus far is able to recognize multiple objects in the frame. In the first frame, you can see a cup is being recognized with a 44% confidence level. We could also see that the bed in the background is being recognized, as well as the table that it is sitting on. We can also see in the right image that we are able to accurately define a person, even though we are only able to see an arm. This is due to the repeated image modeling that is composed of thousands of images that more accurately define what a person is. Here are a couple of snippets of the code that is running the camera and the model that we are using for the project. The framework for these codes are open sourced through official TensorFlow documentation and require tweaks on our end to adhere to multiple guidelines of the hardware that we are using. This is a demonstration of the real-time object detection that we've been working on. As we can see, where the model stands right now, we are able to detect an arm after a couple of seconds. There are some initial incorrect detections that go away quickly, and that is just a result of the frame rate confusing blurry movements as other objects. This will be dealt with in the coming weeks with even more model training. Then we can see the object recognition of a cup as well as a cell phone. Even with slight deficiencies, we are still able to see that the software is detecting correct objects and will need to be fine-tuned to provide even more accurate readings.
So for the challenges that we have at the beginning was to configure the jetpack. However, the successes in the counterpart were that we were able to make it work. The navigation code for the challenges might be a problem because we might not know if it's going to work because the simulation is not really working that well. On the counterpart for the successes, we found that the motors and the sensors using the shield motor actually work for the prototype. These are the use softwares that we use for all of the things that we have been doing. We might end up using all of them, or we might end up eliminating a couple of them just to make it work better. For the final demo expectations, we want to train a finished product. There will be definitely modifications because we know that once we get to the integration part, things are gonna uh, start to escalate in problems, and we might need to change a lot. Uh, Although we may encounter problems, we keep solving it as a team, and we know that for the final demo, that won't be the exception. The integration will be successfully, and we might end up with modifications in the voice integration to accommodate for a smooth working project. These are our software connections for the Arduino, Python, and ROS, which are the main tools that we use to complete our project as of now. And the remaining challenges and conclusions are that well, we need to modify a lot of the things in order to achieve full functionality. We are getting to a point where we need to implement all the parts, especially since we're getting close to the deadline. Uh, those fundamental parts, especially. The stretch goals are still a possibility, but the main focus right now is to make it work and just finish the fundamental parts of the robots. And we want to swap things and components that are not currently working and that might not work when we get to integrate everything. So we want to finish that part and get everything to work. Thank you very much.